Picture an entire city block-sized industrial gas plant with all its treatment columns, heavy pipelines, and storage tanks. Now, imagine taking every piece of that massive infrastructure and placing it onto a single ship, permanently moored over a gas field hundreds of kilometers out at sea. This visualization shows the physical behavior of natural gas. Natural gas is primarily methane, an invisible vapor at room temperature. But when you apply cryogenic cooling and drop the temperature down to -162 degrees Celsius, the molecules physically slow down and condense into a clear liquid. In this liquid state, the methane shrinks to just 1/600th of its original volume. One standard shipping container of this liquid holds the exact same amount of energy as 600 standard units of gas. This extreme volume reduction turns an unwieldy, expansive vapor into a highly dense, manageable liquid. Because of this density, we can load massive amounts of energy onto cargo ships and transport it across oceans where physical pipelines are impossible. This physical property is exactly what allows nations like Qatar to supply energy to Japan, or Australia to power South Korea. Shrinking the gas is the core physical requirement that allows regional natural gas to be sold as a global energy commodity. Historically, extracting that energy required a massive, multi-step supply chain. First, you build a massive offshore platform just to drill the wells, compress the raw gas, and push it toward the coast. Then you have to lay hundreds of kilometers of expensive subsea pipelines along the ocean floor, bridging the massive physical gap between the deepwater well and the mainland. Once the gas finally reaches land, it requires sweeping tracts of coastal real estate. You have to dredge a harbor, secure land rights, and build a sprawling onshore plant with endless rows of processing trains and heat exchangers just to treat and cool the gas. From there, the newly formed liquid is pumped into immense, flat-bottomed cryogenic tanks onshore, where it waits to be loaded onto massive specialized carriers that finally take it to market. If an ocean gas field is too small or sits too far from the shore, the multi-billion-dollar cost of building this entire pipeline and coastal infrastructure destroys the project economics. These are known as stranded reserves. So while the final liquid product is perfectly compact, the physical path required to make it is heavily bloated. Because of this sprawling infrastructure, trillions of cubic meters of ocean energy sit completely untouched. The floating LNG concept directly bypasses this bottleneck. Instead of piping the gas hundreds of miles to a massive coastal facility, engineers pack that supply chain onto a single vessel and sail directly to the wellhead. By mooring right over the gas field, you instantly strip major liabilities from the project ledger. You buy zero coastal land, you dredge zero harbors, and you lay exactly 0 meters of shore-bound subsea pipeline. This drastically cuts the operation's ecological footprint. Structurally, it also creates a unique strategic advantage. When the underground gas field runs dry, you simply disconnect the mooring lines and tow the facility to the next location. Shell's Prelude facility proves the scale of this execution. At 488 meters long, it displaces over 600,000 tons of water when fully loaded, making it heavier than any other floating structure ever built. By reconfiguring the standard industrial process into this dense architectural footprint, stranded gas fields that were previously non-viable become commercially competitive. This cross-section diagram shows the internal layout of an FLNG vessel. To achieve that compression, every facility is mapped into 5 core functions that operate in strict sequence across the topside. Function 1 receives the chaotic mixture of raw fluids coming up directly from the seabed via flexible risers. Function 2 strips that raw input of impurities, removing water, CO2, and heavy hydrocarbons until only a clean gas remains. Next is Function 3, the liquefaction stage. This is a complex central refrigeration cycle that plunges the temperature of the clean gas down to cryogenic levels, forcing it into its liquid state. Function 4 handles storage, capturing the new liquid safely inside insulated tanks built directly into the ship's hull. Finally, Function 5 manages offloading, pumping the liquid through specialized arms onto visiting transport carriers. By stacking these 5 steps side by side, engineers created a continuous, tightly packed sequence. Raw seabed gas comes in one side, and highly condensed energy leaves the other, without a single molecule ever touching land. The combination of high-density liquid and compact engineering has connected isolated gas fields directly to the global energy market. Trillions of cubic meters of natural gas previously dismissed as unviable are now accessible for commercial production. But the physical size of this facility is just the exterior. To understand how these systems operate under pressure, we have to look past the steel hull and zoom in on the microscopic gas itself. In the next module, we follow a single molecule of raw gas through every treatment and liquefaction stage on the vessel. Hit subscribe so you don't miss that breakdown. And drop a comment below telling me which specific FLNG project you want to learn more about. The functionality of this offshore factory relies entirely on the precise chemical reactions happening inside its pipes, and that is exactly what we tackle next.